Okay, good morning and good day to everyone, and welcome to our fourth webinar series from the Boundary System Task Team. Just to let you know, we're having some slight technical difficulties with Dr. Colette Kerry, and she's going to be joining us just now. And we're not sure whether her camera is going to work. But otherwise, we're all here. So thank you for joining us today and to talk about the observing and modeling activities in the East Australian Current. So yes, and also thank you very much to our presenter, Professor Moninya Roughan and Dr. Colette Kerry, for their presentations and for joining us today. So I'm Marjolaine Krug. I'm a physical oceanographer based in Cape Town in South Africa, and I'm the chair of the Boundary System Task Team, and I'll be leading this, moderating this webinar. So today's webinar is the fourth in a series of 6 virtual dialogues on boundary current systems. And the aim of these dialogues is to encourage communications between the observing and modeling communities, and also to provide guidance on the deployment of observing assets at boundaries. So for this, we want to learn from 6 very mature observing systems where you have a lot of capability already developed and many observing assets. And yes, I mean, all our presentations, all the content of the webinars is made publicly available. So this is a resource that you can access at any time before and after the webinars. So just to provide you a little bit of info on how this will take place today. What we will do is we'll provide a brief recap of the presentation, starting with Professor Roughan, and then we'll move with questions from both the Boundary System Task Team and the audience. So while we are doing the webinars, please use the question box and submit your questions throughout the webinars, and we'll do our best to answer them for you. I'll be reading the questions to both the presenters. Okay, so I think we can start now. So I would like to welcome Monia and thank you, and I will let you introduce yourself and give us a brief recap on the observing system in the East Australian Current.
Good evening, everyone. Well, it's evening for me, or good morning for wherever you are in the world, and thank you so much for joining us. My name is Moninya Roughan. I'm a professor of oceanography at UNSW in Sydney in Australia, and I've led the coastal oceanography component of our observing system design and implementation along the east coast of Australia for the last 15 years or so. And so I was asked to present on the East Australian Current and the efforts that have been ongoing to observe the EAC over the last decade through IMOS. I am a coastal oceanographer, and I've tried to represent the satellite remote sensing community and the deep water observations community as well. So forgive me if your favourite piece of observing kit is underrepresented. Let's see here. So just a brief introduction on the East Australian Current. For those of you that are not familiar, this is Australia in the Southern Hemisphere. The East Australian Current comes across the South Equatorial Current and flows down the east coast of Australia, comes to about 32 south and separates off from the coast, forming large mesoscale anticyclonic eddies. And we have impacts of cyclonic eddies as well. We get 7-degree temperature gradients across the front. It's strong, though not as strong as some of the other western boundary currents, up to 2 meters a second, and it really dominates the flow along the coast. It's a very narrow continental shelf, dominates the flow along the coast, impacts our climate and our weather. It's also a global warming hotspot, along with many other western boundary currents, and it's warming at 3 to 4 times the global average down in the southern region. So it's very important that we observe and monitor our boundary current system. And that's been the motivation for a lot of the science questions that we've been doing in the East Australian Current. So just to recap very briefly, the goals of our observing program over the last 1.5 decades have been to understand the mean and the variability of this boundary current. What's the impact of it on the cross-shelf flows, the shelf-ocean exchange, and the biological impact? And then what's the impact of environmental change in the region as well? What's the rate of warming? Is it uniform? And more recently, looking to marine heat waves, the characteristics and drivers. And all these observations are fundamental to answering a lot of these questions. And we use a whole range of different pieces of kit to observe the East Australian current. Looking back now, after 15 years of IMOS, that's our Integrated Marine Observing System, I do think the EAC is a fairly well observed boundary current compared to others. It's by no means ideal, but we're doing pretty well. We have a deep water transport array off 28 South, led by Bernadette Sloyan at CSIRO. That's been in the water for about 8 years now. We have regular XBT lines across these regions here. They're quarterly since 1991. We have continuous plankton recorder lines up and down the east coast. We have long-range HF radar system at the separation point, just one there, and a short-range HF radar system upstream of the separation point. We have a whole swag of remote sensing products from the international programs that IMOS contribute to in the Australian Bureau of Meteorology as well, which is really, really crucial. And then on the shelf, which is where I'm far more familiar, we have mooring arrays at 30, 34 and 36 South across the shelf. The shelf is narrow, about 30 kilometres wide. The moorings are in 50 and roughly 70 or 100 metres of water out across the shelf. And we've deployed gliders along the coast, running down the shelf edge on the inside edge of the boundary current for the last 10 years. We have 4 to 5 missions a year. We're up on mission number 55 or 56. Each mission's about 3 weeks long, and we have very, very regular repeat surveys. We're also fortunate enough to have a long-term hydrographic sampling site that started in 1942, so that is remarkable. It's been occupied nominally weekly for the first 30 years and then monthly since then, and for the last decade we have a mooring at that site as well. So we do have some very well observed parts of the system and other parts that are not as well observed, but are providing critical information. I was asked to provide information on gaps in the system, and one of the gaps that is near and dear to my heart is the southern range, southern end of the system. This region is warming at sort of more than 4 times the global average at the moment. We have this 10 years of temperature records from Narooma region, which shows that warming very rapidly, and that the warming along the length of the system is not uniform. And so we don't have glider observations in this region, so we don't have the spatial coverage or the density of observations that we get from gliders, which is unfortunate. We don't have moorings or anything in the southern end of the system to actually measure the outflow of the EAC. We have our upstream system, upstream observations where the jet is fairly coherent. We aren't measuring the outflow, which could be perhaps instrumented with gliders or moorings if there were loads of money lying around, which there never is. We have moorings roughly every 2 degrees, except in the separation region at 32 South. So that's another gap that we've identified. If we wanted to fill in the density of moored observations, that would be a place to do it. And it would be associated with this HF radar system that we have here. And unfortunately, IMOS have said they're not going to continue to fund the EAC transport array from 2023 onwards. Now, that's a real loss to us and to all of our efforts to observe our western boundary currents and show that these observations are so valuable and so important, not just regionally, but also globally. But unfortunately, the decision's been made at this point not to continue the funding, and we're looking elsewhere to continue that. Obviously, the United States has done very well getting radar along their entire coastline, and that would be wonderful. I think we only have 5 or 6 systems around Australia in total, and more radar would be great. But it's not being used operationally as much as we would like, and that's perhaps one of the limitations here. And if we could actually act on that and get it more operational or taken up operationally, then perhaps we could sell it better. One thing I left out of my online presentation, I realised after I'd recorded it, I was very remiss in not mentioning air sea fluxes, and we are lacking air sea flux observations, and that's something we really need to act on in the future. And then something we are trying to implement further is maximising the benefit from animals as samplers, so increase biologging in the region, seals in the southern half of the system and turtles up in the northern half of the system. So I was asked to provide recommendations, and I think there's always a sweet spot. There's always a trade-off when you're trying to design an observing system between the processes you want to measure and then the actual practicalities of what you can measure. There are issues with site security, longevity, spatial and temporal coverage, and everyone has to really consider those for themselves and what's going to work in their own system. I think a mix of gear provides the coverage that's required. So I really recommend sort of sustained radar at the surface, gliders underneath to give you the spatial coverage and the different variables that gliders measure, and then fixed moorings at high resolution at a point, even if you're just measuring temperature. Again, those high resolution, long-term, sustained temperature observations are really very valuable. And then obviously leverage international efforts. How can you contribute to the International Argo program with 1 or 2 Argo floats, or the International Drifter program? Or how can you contribute to satellite remote sensing programs, developing regional algorithms, or instrumenting a CalVal site, or investigating a crossover point, say with the upcoming SWAT missions? There's lots of things that can be done on a small scale to contribute to that program and then benefit from it as well. I gave the example in my long presentation that analogous observations across boundary currents really allows genuine comparisons. We made a comparison between the East Australian current and the Florida current using high resolution HF radar observations at the same latitude at the upstream extent of those two systems. And it really allowed us to dig into the sub-mesoscale processes going on and show that they actually are quite similar, or more similar than we expected, and that was because we had those analogous observations. And finally, I'd say, Rome's not built in a day. Rome wasn't built in a day, so keep it simple, start slowly, have a vision, work towards it gradually. I can't believe I've been doing this for 15 years now and that we have the system that we have. And honestly, getting that first mooring in was so difficult. So just keep at it, and time passes. So in terms of lessons learned, I'd say now looking back, engage early with industry, work with your stakeholders and ask them, how can we help solve your problems? What are your problems and how can my observing system really help you? That will encourage co-investment and also data uptake. And if people use your data, that will support longevity and your program becomes more valuable the more people that use the data. In my team, we have very tight integration between the people who collect the data and the people who analyze the data, and then the people who are the modeling team as well. And I think that's really valuable. Keep those people close together because they understand the complexities of the data streams, the nuances, and the value and significance of each other's work, and how important it is not to have data gaps. And even during COVID lockdowns, people have gone out of their way to go and service the moorings so that we don't have a data gap in a 15-year time series, that kind of thing. You also get to identify issues and improvements with the data sets more quickly and easily, and challenges. So I encourage you not to work in silos, lots of international, national collaboration and communication and sharing, particularly for small programs that aren't funded well. The more people that work together, the easier it becomes, and it drives innovation and best practice, which I think is great. And tight engagement and integration between the observation and the modelling team. And you'll hear from Colette Kerry very, very soon. She's in our team and leads the modelling efforts for the East Australian current. And I think that tight integration is really important, and it pushes us both, the modellers and the observations, forward. And I've said open access data always. It's been the cornerstone of IMOS, and I think it's really, really important and has allowed us to be so successful. And one of the things we're doing now is moving beyond data sets to data products to try and increase the value of what we do so that more people take up the data and use those data products. So that's a super quick overview of what I covered in my little video. You're welcome to watch the video, but hopefully that reminds people who've seen it of what was covered. So thank you.
Thanks very much, Moninya. That was great. So we're going to move forward with Colette's brief recap. And just please, the participants, please just don't hesitate to add questions even at this early stage, so we have time to look into them. Thanks a lot. Okay, Dr. Kerry, the floor is yours.
Okay, hello, and I apologize that my camera is not working. We're having some little technical issues, but Forrest did put a little photo up on the announcement, so if you want to put a face to a name, you can have a look at that. So yes, as Moninya said, I work closely with her on the East Australian Current and lead the modelling efforts. I've been working on the integration of observations and high resolution modelling in the East Australian Current for about the last 7 years, based in Sydney at UNSW. So if you'd like to go to the next slide, please, Moninya. Okay, so Moninya gave a nice summary of the East Australian Current. In terms of our modelling and prediction efforts, some of the things that we focus on are predicting the strength and structure of the East Australian Current jet upstream of separation, and then particularly predicting where the EAC separates from the coast and how the eddies form and evolve in the complex eddy field that forms in the Tasman Sea. We've also looked at the importance of the vorticity gradient inshore of the EAC on impacting EAC separation. And so some of the model limitations or considerations that I talked about in my talk revolved around model resolution and also the quality of the data assimilation techniques that we're using and which observations are most impactful. So specifically, we've been using modelling tools to study observation impact and then using these results to essentially feed back into observing system design, with the goal of eventually including some of the novel observations that we've collected in the EAC in operational forecasts. So if you'd like to move to the next slide, please. So these are some examples of the observation impact results that I presented in my half-an-hour talk. So we found that observations of the region of highest variability were more impactful than observations in less variable regions. We found that observations in the upper 400 meters were particularly impactful because this is the region of highest variability in terms of the mixed layer and the thermocline. Observation platforms that were particularly impactful were the deep water mooring array off of Brisbane, the gliders that sampled eddies in the eddy dominated region of 34 South, the high frequency radar array, which is measures surface velocities of 30 south of Coffs Harbour, was particularly impactful on estimates of EAC transport and eddy kinetic energy both up and downstream of its location. And gliders on the shelf, and particularly gliders that sampled eddies offshore of Sydney, were particularly important in constraining the subsurface structure of EAC eddies. So could you move on, please? So in light of these results, we've come up with some suggestions for further observations, and we're presently doing some observation system simulation experiments to test these recommendations. So as I mentioned, we found observations taken in regions with greater natural variability are most impactful. The high frequency radar, the deep water mooring array, and the deep gliders were particularly important in improving our estimates of the EAC circulation. And because we're using sort of variational time-dependent techniques, our observation impact was far-reaching both up and downstream, forward and backward in time. And so we're looking at observing system simulation experiments where we comparing sort of sampling upstream, where the EAC is typically most coherent, compared to sampling downstream in the energetic eddy field. As Moninya mentioned, the funding for the mooring array will be ending soon, so we're looking at whether we can get similar sort of results by doing repeat glider transects across that location. And then also we have that now long-range high-frequency radar array, which measures the eddy-dominated region downstream, so looking at the impact of that versus the high-frequency radar array upstream. So we can move on, please. Okay, and then in summary, just some suggestions for advances in modelling techniques, with the goal to eventually include these novel observations such as the gliders, the high frequency radar, and then the upcoming SWAP missions. Operationally, we're working towards using these advanced data assimilation techniques, so either 40VAR or ENKF, which is being developed by the Bureau, and having some discussions about hybrid methods, so using ensembles to come up with flow-dependent covariances that can be input into the variational methods. Particularly in the EAC, the challenge is representing the eddy structure, so we're looking at how we can better tune the system to represent eddy depth, eddy interactions, and things like that. And then we've done some higher resolution work on the continental shelf and found that errors are typically dependent on the parent, so the parent model. And so rather than using data assimilation at this level, we're looking at better model tuning to forecast these fine scale features, and looking at doing that potentially with parameter estimation in the 40VAR control vector. So those are some of the advances that we're hoping to make in the modelling techniques. And then in summary, the final slide just shows a summary of how we're sort of integrating this observation impact work to use models to inform observing system design. So it's sort of a full cycle where, as Moninya said, we're all working together, the observationalists and the modelers, to feed back into observing system design and hopefully eventually feed back into operations with our collaborations that we have with the Bureau of Meteorology. Yeah. So yeah, that's it for the summary. I guess we can go on to the discussion.
Thanks very much, Colette. That was really useful. I must have really enjoyed watching your presentation and looking at the way in which you've gone into a lot of effort to establish which observations are useful in which region and how the impact of observation on the modeling. So I would like to actually follow up on that and put forward a question that was asked by one of our team members, Dr. Kiyoshi Tanaka, about the vertical structure and why you're struggling to represent that vertical structure in your models without the assimilation. So I'll just read the question that Dr. Tanaka has put forward. Why is it difficult to reproduce baroclinic structure of mesoscale without data assimilation? What dynamical processes are lacking in ordinary prognostic simulations with coarse resolution model? And is there a hint about how submesoscale variability, such as point instability or bottom boundary process, would affect the formation of the mesoscale baroclinic structure? So it's a bit of a long one, but if you can just expand on what you think needs to happen on the modeling side to better represent these vertical processes.
Okay, so I guess there are two things. The first is our free-running numerical model does a very good job of representing the baroclinic structure of the East Australian current core and eddies. And when we introduce data assimilation, when we're only assimilating surface observations, that's when the subsurface structure of the EAC and its eddies is not well represented. So this becomes an issue because then when we do assimilate subsurface observations, the baroclinic structure is really only well represented when the observations are available, and when the subsurface observations are not available, then that subsurface representation is then poor. And the way that this needs to be addressed is better tuning of the data assimilation system, and in particular the background error covariances. So as it stands, we don't include balanced operators in the background error covariances, and we're also working on sort of constraining those covariances more at depth, because we're getting too much adjustment in the assimilating model at depth. And so this sort of causes a breakdown of the subsurface structure of the EAC core and eddies. So it's not fundamentally an issue in the free running model. The dynamics of the model are correct. It becomes an issue when we try to assimilate data and the adjustments that are being made are not doing so correctly throughout the vertical structure of the ocean. And this has also been found with other data assimilation methods in the region. So our colleagues at the Bureau of Meteorology and CSIRO are using ensemble optimal interpolation, and more recently ENKF, and they're having similar I guess problems representing the subsurface structure. So that's something that we're working on. But yeah, it really does come down to the specification of the background error covariances, which is probably one of the biggest challenges in DA today, is getting those right. Yeah. I hope that answers the question.
Yeah, great answer. Great answer. So it's the complexity of data assimilation is probably, there's a lot of research that needs to go into that. Thanks very much for your answer. I'll just follow up also with a question from Tanaka. Just to remind our audience, please don't be shy and ask some questions. So you've been very quiet today. But I'll just follow up with some questions from Dr. Tanaka to Moninya about the use of the satellite in the observing system. He's mentioning that in Japan they have the geostationary satellite Himawari 8 that's been used by the Japan Meteorological Agency, which can capture sea surface temperature and chlorophyll with a very high spatial resolution of about 500 meters to a kilometer, but also a very high temporal resolution, about 10 minutes. And he says he's heard that the Australia's Bureau of Meteorology is using it to watch forest fires, and he's just wondering if it's useful for marine observation as well in Australia. I know you've got, Moninya, you mentioned there might be people in the audience better placed to answer these questions. I can look to see if I see them, but I'm not sure whether I can unmute them. It might be possible. Forrest, if you can just advise if that's possible or not.
I did get a heads up on this question, which was great. And so I sought insight from my colleagues, Edward King at CSIRO and Helen Beggs at the Bureau of Meteorology. So if either of you are online, you're welcome to answer. But in the meantime, they asked me to let you know that we absolutely are using the Himawari 8 data, and it is a game changer. One of the benefits for me of IMOS is that I'm just delivered satellite remote sensing products by all these teams who do all the really hard yards, which is why I had to get insight from them. So the IMOS has a satellite remote sensing facility, and Helen Beggs leads the SST component of that, I believe. And they've been producing satellite SST products for the Australian and Southern Ocean region since 2008, and they're reprocessing data all the way back to 1992. And they've got a whole range of different products, operational, real-time and reprocessed SST products using the polar orbiting satellites, also AVHRR and VIIRS, infrared sensors, etc. And also experimental products such as 10-minute hourly, 4-hourly and daily Himawari 8 level 3 composite products. And Edward reminded us that 144 images a day poses a huge volume challenge, and so compositing is required, particularly if we need to archive the data. But he also reminded me one of the big advantages of Himawari 8 is when you have 10-minute data, you have a lot more opportunity to see through gaps in clouds. So, that's one of the major problems with remote sensing, and that with the frequency, high frequency sampling, you just have an opportunity to gather more information, which is really, really fantastic. So can you see, are either of them able to contribute, Marjo? Were they there maybe?
I know Helen Biggs is here. I'm just trying to see. I'll ask Forrest if she can maybe unmute her. Yeah, I'm not sure how to unmute her. She's got maybe Forrest, if you can give her some rights. But in the meantime, I'll just follow up on that, because with the availability of such products at 10-minute resolution, you can anticipate that maybe some of these products can be used for. I guess that's a question for both of you. Do you anticipate that these type of products would be able to be used in the data assimilation
one of the challenges we're grappling with at the moment is how to derive benefit from future satellites. And SWOT mission is a great example. There are a lot of people using synthetic SWOT data at this point to understand how to assimilate it. And even with regular long track altimetry data, we're still having trouble trying to assimilate that in the EAC region, for example, and Colette can follow up on this. If you've got 3 tracks across the entire boundary system in a day, it's very hard to assimilate it and get the eddies right. Do you want to comment on that further, Colette?
Yes, I think in terms of the high temporal resolution sea surface temperature data, there's definitely potential to assimilate it, given that we're moving towards these sort of more advanced time-dependent methods such as 40 bar and ENKF. And it can be particularly useful because, as Moninya mentioned, sometimes the sea surface height data is quite sparse, given that we're relying on only several tracks passing in a week, for example, sometimes. And so there's definitely scope to make use of this sea surface temperature data, which can feed into the data assimilation system in terms of getting the eddies in the right location and things like that.
Yeah, would you like me to, sorry?
Yes, please, Helen, go ahead.
Yes, sorry. Yes, we are, as I've put in the chat here, we are particularly interested in cold upwelling, especially along the East Australian coast. So we are actually looking at that. I did present a poster in 2019 or 2018 on this, but recently we've started to look at it again, especially with colleagues who are using eco-stress instrument on the International Space Station, which is 70-metre resolution, which is really exciting. It gets right into the coast, right onto tidal mud flats, and it goes over land, of course. It's land surface temperature. So over the ocean, its algorithm is not ideal. They, at Uni of South Carolina, the guys there who work on eco-stress SST, they are going to try to develop a more accurate SST algorithm so that it works better over the ocean. But this is a wonderful tool for validating ocean models and also other satellite SST products. And they are now looking at coastal upwelling regions around the world, such as Peru and Spain, but I'm also trying to get them to look at the Australian coast. So what I'm trying to say is, are you interested in coastal upwelling, I guess, along the East Australian coast? Is that of interest?
I would say absolutely. You know, western boundary currents are typically oligotrophic, so understanding the processes that drive productivity on short timescales are very, very important, particularly in the southeast Australian current region. So absolutely, and I'm sure more broadly in other western boundary currents as well.
Okay, because the challenge that we are looking at is that every agency that produces infrared satellite SST products, they cloud clear their satellite data differently, and the various products behave differently, especially in cold upwelling regions, which they often may flag as cloud. Some do, some don't, it depends. But anyway, that's something which we are looking at, because if you want to study coastal cold upwelling, often it's cloudy anyway. It's real cloud, so you don't get the satellite infrared data. You don't get the microwave data because you can't see anything to within about 50 meters, 50 kilometers of land. So you are limited pretty much to infrared. and that is affected by clouds, and it's masked out by the, often it thinks the cold upwelling signature is cloud. But yeah, Himari 8 does help there because it takes a snapshot every 10 minutes. So depending on how well you can identify cloud in Himari 8, if the clouds move, and then you do get much greater spatial coverage around the coast. And it's a wonderful tool, and it's something that we are investigating at the moment, comparing with all sorts of different satellite products.
Thanks very much for your input, Ellen. It's actually quite useful because there was a question asked by Sam-Yong Kim about, which platform observation or the resources are required to investigate the interaction of the regional boundary current with the coastal systems and coastal submesosphere processes, eddies, fronts, but also looking, at really those links to the coast. And I guess this is, in your region at least, you have some exciting development that maybe those kind of observation will be able to fill that gap in bridging the boundary to the coast. But what other observation do you think, and that's a question for Moninya, what other observation do you think are needed in order to better resolve these links to the coast?
So our shelf is narrow. Upstream of the EAC separation point, it's 20 to 30 kilometres wide, and the jet sort of flows along the 1,000-metre isobath. We have high resolution HF radar up off Coffs Harbour at 30 degrees south. So it's 1 kilometre resolution, and the range is about 100 to 150 kilometres offshore. And that is enough to see to the back side of the core of the jet, which is phenomenal. But what we've also been able to see for the very first time with that radar system is the variability on the inner edge of the EAC jet. So we're starting to see the development, the spin up and the evolution of frontal eddies, so small cyclonic eddies that form on the inside edge of the current, and they advect downstream. So we don't have a whole row of radar systems, which is unfortunate. So we can only just monitor this one location. It's about a 100 kilometre square patch. And we did some work that showed that these sort of sub-mesoscale eddies, they grow and they form every 14 days or so. So I would say high frequency, high resolution HF radar is very, very important. And I kind of feel like that was a loaded question from Sam-Yong Kim because he's a radar expert. But it really does benefit us and our understanding. But having the moorings beneath that radar system is also important, and the gliders that then give the spatial evolution of the eddies. And we've used these 3 different platforms together. I think Colette can also comment there because we did some work trying to assimilate these data at high resolution. Wasn't as successful, and she touched on that. So Colette, what are your thoughts on resolving the sub-mesoscale?
Yeah, so I'd just like to say I think the HF radar has been really fantastic in terms of being able to assimilate that into the regional model of the EAC, and we've seen some really significant impacts on improving the representation of the vorticity gradient inshore of the East Australian current, and that had effects sort of both up and downstream of the actual HF radar location. In terms of predicting the specific timing and location of these sub-mesoscale features that do form inshore of the East Australian current, this was particularly challenging. So we went to an even higher resolution to try and resolve the sub-mesoscale inshore of the EAC, and the actual predictability was challenging, and so we're hoping to work towards sort of model tuning rather than data assimilation at those fine scales. But from a sort of regional modelling perspective, the HF radar was particularly important in getting that vorticity gradient right. Yeah.
Thanks, Colette. You mentioned also, the importance of the mooring array led by Bernadette, and obviously we're very concerned that the funding's been discontinued for that, and that this array is actually quite key in enabling you to locate the core of the current at the right position and the vertical structure as well. I would anticipate that the mooring array is actually also really useful to look at longer time scales on the seasonal to interannual, decadal viability, etc. In your modeling experiments, are you looking at so this is really just to follow up on a question by Janet. She says some of the models are predictive or forecast models that can help guide seasonal prediction for climate, water, fisheries management. Has there been an assessment of these predictions, of how successful these predictions are, and what are the remaining challenges that might lead to improvement? And do you think that not having these continuous time series that would really impact on these longer term forecasts?
Right. So from our modelling perspective, we haven't directly been looking at seasonal and longer term projections, but we have studied sort of relationships between the strength of the East Australian current at seasonal timescales, since the strength and the eddy variability of the East Australian current at these seasonal timescales, and seen relationships between upstream East Australian current transport and downstream sort of eddy kinetic energy and things like that. So, but in terms of seasonal predictions, that's been more sort of covered by our colleagues at the Bureau of Meteorology and CSIRO. But I think these long-term observations are definitely important to understand seasonal variability. So we've used a sort of long-term free-running model to look at seasonal variability in this East Australian current, but validated that with some of these long-term observations, and they were really important in that sense. So yeah, losing them is definitely a great shame. But yeah, I'm not sure I can do a great job of answering the question about seasonal predictions, because we're more focused on sort of the mesoscale eddy timescale, so predicting eddies as they shed and as they evolve. Yeah.
Can I comment from an observing perspective? I think there is a danger in trying to sell these data streams as only being useful after a certain amount of time. Funding agents don't like to hear that, or funding agencies don't like to hear that. So you have to do the process studies along the way. 1 year of data is more than most people could dream of. And so there are loads of studies you can do. The assimilation system that Colette demonstrated used 2 years of data, 18 months of data from that transport array from 2012 and 13, because that was the very first 18-month period we got. And we're still using that assimilation, those 2 years. There's so much we can do with just that 2-year period. And all our first data assimilation papers are based on that, and we keep nesting inside that model and testing it and getting answers from it. So we don't need 10 years of data to prove the validity of the data, but you do need that really long time series to understand changes in the system. So it's a fine line. And I think perhaps if people don't see the value of these data streams until they're 10 years old, you run the risk of not being funded.
Yeah. That's a good point. Yeah, and you mentioned, Monia, in your presentation that as the years have gone past, you've actually starting to interact more with stakeholders in industry. And I was just wondering how you've done that, and what was the feedback from these industry and stakeholders, and if you can elaborate on some success stories that you've had, and how do we get those industry and stakeholders to contribute, to sustain the system?
It's a challenge, and I think some groups, some countries, some regions do it better than others. In the beginning, IMOS was very fortunate that it was funded as a research infrastructure and through a national research infrastructure scheme. And we have evolved over the last 15 years. Even though we're still a research infrastructure, we're now being measured by our impact and our engagement with stakeholders, where initially we were measured by the number of publications and students and data streams, research data streams that we produced. And so it has necessitated a shift in mindset. And honestly, for university academics, that can be a real challenge. other countries, I spent some time in New Zealand engaging with industry quite closely. They're much better at it because they've been forced to. They would argue that funding is tighter, so they had to go to stakeholders initially and sit down with them and say, what's your problems? How can I help you? And then they focus their research programs around that. So different groups are better at it. Societal benefit is front and center now for everything that we do, and everyone's pivoting to, the coastal oceans where societal impact is greatest. From my perspective, very eager stakeholders, the seafood sector. They're being impacted by climate change faster than they can understand. They don't know what's going on with fish stocks, abundances, distributions, etc. And everyone wants to relate their favorite animal with environmental variables. What's the temperature? What's the chlorophyll? What's the stratification? What were the eddies doing? And how does that impact on my lobster larvae, my bull shark, my great white shark, my turtle, my whatever it is, their favorite biological organism? So that's an easy win. So data products that can be easily related to abundance of something, or fish catch, or distribution. And that really provides value and impact for fundamental observations of temperature and ocean circulation and so on and so forth. So for me, that's an easy win. Others are ports and harbours. Up off the Northwest Shelf, there's a lot of oil and gas investment. I believe they've invested in a HF radar system, co-invested with IMOS. Instead of going out and buying their own system, getting their own technical staff and deploying it themselves, they're managing it themselves. They said to IMOS, how can we partner with you? How can we use your expertise to deploy this system and deliver the data through your portals and systems? So that's a different way of getting co-investment as well. I think we're a big country with a small tax base, so we don't have a lot of money. So getting that kind of co-investment collaboration is really very important.
Yeah, and it's quite a big job to get, to mediate between those two different groups, the scientific community and the users and the industry. And I would argue that it's a bit unfair to put that on the scientists, and that they should actually be people whose work it is to do that, and that could help in actually maintaining those systems and really showing how important it is for those people to answer some of these questions and their concerns, and make sure that they can continue to be sustainable use of the ocean. But anyway, that's a little bit of a side note. I was wondering, it's actually a question for Colette. Not everybody or not every country has developed such expertise in data assimilation. I mean, I know in South Africa, where I'm based, we don't really have that capability yet. We've developed a little bit, and then our expert Bjorn is actually attending the webinar today. He left overseas, and we're trying to develop new capability on this. But essentially, the approach we're having at the moment is to use the global models to force regional models which don't assimilate observation. So the observation is only assimilated in the global models. And you've shown in your presentations how important the HF radar and the gliders are in the data assimilation. And I know there's global effort to coordinate these observations as well. Do you think we will have in the future HF radars and gliders assimilated in those global models, so that there is a real improvement? And what would be the impact of doing that?
Yes, I think an ultimate goal of the global modelling community would be to have, so we talked about this at the recent Godet Ocean Predict meeting, in that particularly in western boundary current regions, an ultimate goal would be to have sort of two-way nested regional models where we have a higher resolution in the western boundary current regions, and we're able to assimilate some of these novel observations that are particularly useful in the western boundary current regions, such as HF radar and gliders. Because at present, one of the greatest challenges of the sort of global modelling community is representing the western boundary current regions. So I think whether it will happen or not, I'm not sure, but I think it's definitely something that the global modeling community are hoping to work towards, is yeah, doing that, but particularly in the western boundary current regions. So obviously that impacts you in South Africa. Yeah.
Yeah, I think those efforts to coordinate the data collection and make sure that we have proper quality control of the data streams has really led to major advances. And that's one thing that IMOS has done very well, is to provide this data platform and to make sure that the people could access the data, that you had an open data policy. And I'm all for open data policy, but many people are very reluctant to share the data. How did IMOS manage to change the mindset of people and actually push people to share the data and to create that open data policy framework?
So I guess if you go back 15 years ago, that was the buy-in. If you wanted money from the program, you had to make the data available, and we have strict milestones on how quickly we have to make our data available. So within 3 months of retrieving our moorings, I have to have all my data downloaded, QC, quality controlled, converted to CF compliant, IMOS standard NetCDF files, and delivered to the portal and made available. And we do that in about 10 days now. We've got it all down pat and we just do it. I guarantee you, no one's going to do the study you were going through. We're not curing COVID here. We're studying temperature in the ocean, right? No one's going to gazump you on your favorite study of your favorite piece of the ocean. I really believe that, especially in coastal oceanography. There is so much data now. I have 10 years of data in southern New South Wales, and it's quite, we haven't published enough papers on it, so it's all there, it's all open access, anyone can use it, and the more people that use it, the better. Case in point, we have co-investment from Sydney Water. That's our local water treatment, water provider, and they have to measure ocean temperature and stratification as part of their license to pump processed sewage into the sea. And they have delivered all their data to us, to the IMOS portal, but they were not willing to make it publicly available without people signing a waiver saying that they wouldn't use it against them. And so we could not make that data available. And just this year, despite the fact they delivered it to IMOS routinely every year for 10 years, just this year they've now signed an agreement that data can be made available with a Creative Commons license attached. So those Creative Commons licenses are really quite important, I think, for giving people the freedom to make their data available as well. So all IMOS data is now made available under Creative Commons licenses, I believe. So that was quite a breakthrough for us, because that is one of the longest time series. It's a 30-year time series off the moored time series off the coastal ocean of Sydney. So back 15 years ago, there were people that said, I don't want to play, I don't want to make my data available. And 15 years on, they look a bit silly. They didn't get involved, they're not making their data available, and they've been left behind. Everyone's moving to open data. Journals are requiring it. Every review I get back on a paper now says, oh, good, data's available, that's fantastic. I think you just got to embrace it and go with it.
I agree, and I'm completely with you on, we've got so much to do already, like we don't have time to look at someone else's data.
Yeah.
But and as you say, you gotta, luckily, with many of the funding now is provided on condition that the data becomes available within a certain time frame. So I think that's also a move in the right direction. I'm going to ask another question, like a little bit different one, before we get into the end of this discussion. It's been really lots of fun. You have managed, you say you've managed to have a lot of communication and to really work together between the people who collect the data, those who analyze it, those who do the modeling and the data assimilation. And that's really, I think, a good lesson for us to learn. But I was wondering, how is your interaction with groups that deal with biogeochemical models or biology, chemistry of the seawater? Do you also have those channels of communication with these groups? And of course, we're only reviewing here the physical observing system, but I know there's a lot more that is observed, and I'm sure it's connected in some way. So how do you do that as well?
I think first I'd say, I think I've said before, we're a small group, we're a small team. Everyone's got their little niche. I had a student who was supervised by a world expert on biogeochemical modelling, and together we built a biogeochemical model of the EAC system, and that's how we do it. We partner with experts. We didn't have a modelling program until we got some funding to bring Colette on, and 7 years later she's still with us. So like I said, Rome wasn't built in a day, but we baby steps. We've got one person now, we've got 3 or 4 modelers in our team, and we've been able to grow the effort, and finally I feel like we're at critical mass. So we do work closely with biogeochemical modelers at CSIRO and observationalists as well. It's probably an area where we're under-resourced. We've got more effort in further up the food chain, larval fish, and obviously the charismatic megafauna, etc. We can only do so much, but we just keep chipping away at it. So, yeah.
Yeah, I suspect it's not always easy when you are a much bigger community in some regions to coordinate those different efforts. So in generally advising, like, how have you got tips on how you can help do that, create this coordination between the modelers, the observers and biologists, the different communities?
Communication, regular communication, I think, really important. I think now that everyone's working online so easily, it actually makes it easier to communicate and quickly have a Zoom with someone or send them a message on Slack or whatever. Just build those collaborations and keep the communication going. I think it's really important. And obviously money really helps.
I guess I'd like to say Moninya sort of has made a conscious effort to organise workshops. So we've had EAC workshops where we bring together sort of all of the different organisations in Australia who are working on the EAC, observationalists and modellers. And it might only be a few days where we all get together, but those collaborations that we've built during those workshops are really useful when we all go back to our desks and knuckle down to what we're doing. So just things like that. I think building a tight-knit community is really important.
Yeah, and I think with the focus now on societal impact being so strong, that you kind of force into these multidisciplinary projects as well. Maybe. Anyway, so we actually it's 11 o'clock. Well, 1 hour's gone already. So I'm going to close this and just wanted to say thank you so much for being there. Thanks to all the participants who have joined us, and thanks to Forrest Collins from the WMO who has assisting us in setting this up. And yeah, we look forward. We've got 2 more webinars coming. The next one is on the Gulf Stream, and it will happen not next month, but in October, on the 6th of October. And so keep your eyes peeled for this, and they advertise through the Bruce website. And you also invited to access all the previous webinars that we've done. If you're interested, there's been some on the California current, Horatio, and the Abelian system, and they're all great. So thanks again for joining us today, and be safe and take care.
Thank you.
Thank you.
Very much for having us.
Bye.
Bye-bye.